Right now, I explain the introduction uh, of transfer functions. Right. In the student of advanced electrical circuit, the transfer function play a crucial role in analysis and understanding the behavior of electrical system and in the frequency domain. A transfer function, typically denoted as H S or H J omega, is mathematically represents that related the output of a system to its input, allowing us to determine how the system responds to different frequency. It is especially useful for linear time invariant LTI system and form the foundation for designing an inverting filter, amplifier, and control system. To visualize the frequency response of a transfer function, engineers commonly use the pot plot, which is consisted of two graphs: the magnitude plot in decade and the phase plot in degree. Both plot again logarithmic frequency. The pot plot simplify the progress for predicting system performance, identify critical frequencies such as pool and zero, and estimating system stability. Together, transfer functions and bot plot are essential tools that help engineer design and analysis complex electrical circuit efficiently. Right. That's all the introduction for transfer function. Hi, right. My name is Muhammad Faris Zainab bin Azra Anwar. My number metric B1124-10-424. Right. Today I explain about part B, transfer function. Looking at example transfer function in frequency domain, right? H J omega. Okay, as you can see, this is original transfer function. Common found in filter circuit like low pass or band pass filter. Right. Okay. To what we want to do is convert this into a form that easier to plot using bot plot. To do that, we want to rewrite each term, so we likely j omega per omega c plus 1, where omega c is corner of break frequency. Right, let's start. Let's start to numerator j omega plus 10. We multiply and divide by 10 to get j omega per 10 plus 1. Next, we looking at numerator. J omega plus 5 to the power of 2. And again, we want to express j omega plus 5 in the form j omega per 5 plus 1. So we multiply and divide by 5. Just like that, j omega per 5 plus 1, 5. But since it's square, we write power to power. Power j omega per 5 plus 1, 5 to the power of 2. Right, after simplify everything, we can get this final. But I forget this 0.4. 0.4, what you get after you 5 to the power of 2 per 10, and you can get a 0.4. 0.5 is a gain. Gain or gate, like that. Similar like that lah. Okay. So with this final form, we can now continue with frequency analysis much more easier. And that's all for my part. And now I give Faris Fahmi to explain about the graph bubble.
Hello and a very good day. My name is to Muhammad Faris Fahmi bin Arman, matrix number B1124100394. And in this video, I will explain about the transition from my friend's explanation video about transfer function. And in this video, I will explain how to draw the Bode plot based on the transfer function that you've got on the calculation. So before you do anything, before you even draw anything, I would suggest you to calculate the gain value first. So how to calculate the gain value, or K, you would use this formula or equation here. So 20 log 0.4, where we're using this value over here, and then you're gonna get the negative 8 decibel value. So before you draw anything, I would just suggest you draw this 0 decibel line first, so you don't get as confused. And each of this um, partition here represent 2 decibels. So if you go up here, it's 2 decibels, 4, 6, 8, 10. If you go under, it's going to be negative value, so -2, -4, and so on. And after that, you draw your -8 decibel line, or your gain line. In my graph, I use the color pink here to represent the -8 decibel value. So I'll show you. So this is the first function after the gain. We're gonna show you this one next, j alpha over 10 plus 1. So if you refer the schedule here, it's gonna be simple zero function. Simple zero function meaning that it's gonna go up 20 decibels. So the way to draw it is you need to first to draw it until 10 point here. Why 10? Because if you look at the function, it's over 10. So you need to draw the line until 10 here, where they meet, and then go up 20 decibels. So that's the first function, and then make sure that you write down the function here so you don't get it confused and all. And then the second function is we go down here. The value down here, all of them are negative value, meaning that it's gonna go down. So we look at this function here is j alpha. Okay, we're gonna refer back to the pole at origin, meaning that it's gonna go down 20 decibels. So if you break this down, this equation here is gonna be 1 over j alpha here, and then this one's gonna be 1 over j alpha 5. It's not w, it's alpha plus 1 and square. So it's gonna be like this. If you look at this function here, 1 over j alpha is actually pole at origin, so you're gonna need to go down 20 decibels. But for this function or factor, you need to start at the number 1 point here. You need to draw it the number 1 point here. So on my graph, I've used the color of, I believe, yellow here to draw the pole at origin, or 1 over j alpha function. So like I said, it will go down 20 decibels. So you would pick a point here, which is 0.1, and then you just basically just draw it from here to 20 decibel here. Drag it over here, make it like a straight line. And then you write down the transfer function here so you don't get it mixed up. And then for the last function is 1 over j alpha over 5 plus 1 square. So this is simple pole function. So simple fold is this one here. You should go going downwards because it's a pole value, not a zero value. So it goes down 20 decibels. For this instance, you look at this denominator is 5. You should draw the line at 5. So you drag here to 5.5 here, and then you draw down 20 decibels here to here. And we're not done here actually. The last part is count. You need to count the critical point or the important points for this pole plot. You could choose actually any point down here. In my case, I would choose critical point at 0.1, critical point at 1, 5, 10, 50, and 100. Black line here is representing the critical point that I did. So for the critical point at 0.1, so you need to calculate it by looking at this as a straight line here. Count where the line intervened, meaning that if you can see here is 20, where they get the value 20 is from actually here, because it's intersecting with the 0.1 value. So you need to add them up. 20 plus minus 8 is the gain value is also intersecting at our 0.1 line here. So you add it up, it's going to be 12 decibels. And then this is where you start your critical point. So the next one is 1. Critical point 1 is, you look this one as a straight line and find the line that intervene with this, one of these four functions line that intertwine with it. Basically, if you look this as a straight line here, the only line that cross it is this negative 8 decibel value. So just put it in 0 plus negative 8 decibel value, so you get negative 8. So at one critical point at 1, and then you just assemble them basically. Same goes to critical point 5. You just look this as a straight line and then watch where's the line that intervene with it. So you just calculate it, put it into this, and then I get negative 22. So I just put a mark here and then just draw a straight line there. Same goes to critical point at 10. Find the line that intertwines or goes through at point 10 line here, and then you just add them up. So I get it's actually negative 34 here. It's 4 here, and then same goes to critical point at 50. I would do is just, look at it very carefully and then do it multiple times. So critical point at 50, 0, our 0 decibel line, and then our gain line, negative 8, and then negative 18. I get it from here. So this is negative 8, our gain line here. So this is, like I said, one of this line represent 2 decibels. So this is 8, and then 10, 12, 14, 16, and 18. So that's your 18, negative 18 decibels. For negative 32, should do same thing. So this is, you should count from this line here, 0, and here that intertwined with this line. So this is 0, this is 10, 20, up to this point here. So 30, this 32. This you got negative 32 value. So add them up, you get negative 58. So that's the critical point at point 50 here. And the last one is the critical point at point 100. So this is the 0 decibels here, starting here. So 2, 4, 6, 8. So negative 8, 10, negative 10 decibels, negative 20, and then negative 30 here. So this is 32, 34, 36, 38. So that's the negative 38 value. For this is the gain, negative 8, because it intertwined with the line here. So negative 100 is line here. I'm gonna write the line. So it's intertwined with the 100 point here. So you're gonna count it too, and I put it in the equation here. So you got negative 8. For the negative 24, same thing. This line here. So this is 8, 10, 12, 14, 16, 18, 20, 22, 24. And then you get negative 24. Add them up, you get negative 70. And then after you got all the critical points, just need to like draw them up nicely. So thank you.
Hello, my name is Arasu Annalaki Poindren, and my matrix number is B1124106002.
Hello, my name is Wan Muhammad bin Nasruddin. My metric number is B1124103991.
Eh, kau cakap kuat sangat. Sini tak dengar.
Kau dengar?
Kuat-kuat sikit. Okay?
Serius lah, tak dengar.
Ulang lagi sekali. Kau
Sekejap,
baca
sekejap.
kuat sikit. Macam tak dengar je.
Sekejap.
Okay, guys. Boleh start kan?
Sekejap, sekejap. Sekejap, sekejap. Dengar tak?
Okay. Hello, my name is Arasu Annalaki Poindren, and my matrix number is B1124106002.
Hello, my name is Wan Muhammad bin Nasruddin. My metric number is B1124103991.
Today, I will present the analysis of a dot plot and how we can determine the system transfer function based on its frequency response. So, let's begin by observing the given dot plot. This plot shows the magnitude response of a system in decibels versus frequency in radian per second. So now I describe about the dot plot. From omega 1 radian per second to 10 radian per second. The slope is positive dB per decade, which means the slope is at going to 20 dB. So next is from 10 to 50 radian per second. The slope is flattened at 20 dB, meaning 0 dB per decade. After 50 radian per second, it drops with a slope of negative 20 dB per decade. So now I explain each steps. First is to find the gain value. So to find the gain value, the flat portion of the plot is at 0 dB. So using the gain formula, 20 log k equals to 0 dB. We find k equals to 1. This gives us the constant gain of the system. So the value of the k is 1. Second is a 0 at origin with slope positive 20 dB per decade at omega 1, which means the plot start rising at positive 20 dB per decade from omega 1 radian per second. So this tells us there is a 0 at the origin contributing a term of j omega in the numerator. Third is a simple pole with positive 20 dB at omega 10 radian per second. So means at omega 10 radian per second, the slope drops to 0 dB per decade. This is caused by a simple pole contributing the term 1 divided with 1 plus JW per 10, which means a simple pole with positive 20 dB at omega 10 is equals to this equation. So number 4 is a simple pole with negative 20 dB per decade at omega equals to 50 radian per seconds. So means at omega 50 radian per seconds, the slope drops to negative 20 dB per decade, indicating another simple pole. This adds the term equal to 1 divided with 1 plus j omega divided with 50. Next, I pass to Wan to continue about the transfer function.
All right, thank you, Alasu. So let's simplify the given frequency response function of omega. So this is typical transfer function in the frequency domain, where is J is the imaginary unit and omega is the angular frequency. So to simplify this expression, we multiply the terms in the denominator by their respective constant, which is we need to divide and multiply the first bracket with 10 per 10, and the second bracket we need to multiply and divide with 50 over 50 over yes. So to the next part, we need to bring out the constant, which is 1 over 10 and 1 over 50 to the outside, which is we can get, yes, we need to multiply this. And then we get the 1 over 500. And we need to transfer the 1 over 500 from denominator to the numerator, which is at the front. So we get the 500 j omega over 10 plus j omega, this second bracket, 50 plus j omega. So the j omega we need to convert to the s, which is the meaning of s is, which is the meaning of s. What?
Complex frequency.
Complex frequency. Yes, complex frequency. Yes. Thank you. All right. Thank you also.
Okay. Then now I show the Bode plot. This is proven for the below above answers, because as we can see, for each point we must add, which means plus. So for each point the total dB, so from that we can plot the final line. So the final line from the Bode plot is same as the in question given. So that means our calculations is correct based on Bode plot that we did. So this is the proof that we did to find the transfer function. So now I pass to Wan to conclude our question F.
All right. In summary, by analyzing the slopes and corner frequencies in the Bode plot, we identify a zero at the origin and two poles at 10 and 50 radius per second. From that, we successfully construct the full transfer function of the system. So we calculate, we can get this Bode plot. So this Bode plot tally with the question. So our calculation is correct, right, Arasu?
Yes.
Yes. So that's from us. Thank you.
Thank you.
Hi, it's Mohammed Faris Fahmi again, and I will talk about the discussion part, which contain the observation and result from the assignment. From the analysis and simplification of the transfer function, we were able to break down the system into its basic component zeros and poles, and observe how each affects the overall frequency response. The Bode plot provided a clear way to visualize these effects, showing how the system gain and loss change with frequency. In this case, the presence of a zero increased the slope of the magnitude plot by plus 20 decibels per decade, starting from its corner frequency, while each pole introduced a negative 20 decibels per decade as it increased. As a result, the system initially shows a gain increase, but at higher frequencies the poles dominate, causing the gain to drop. This analysis is important because it helps us understand how a system behaves in response to signals of different frequencies, which is essential in control system and filter design. Overall, the Bode plot serves as a powerful tool for predicting stability, system performance, and for designing compensators or controllers. Thank you.
In conclusion, in this assignment, we learned and understood the frequency response characteristic of linear system using Bode plots. We begin by simplifying the given transfer function by showing how it can be expressed in terms of its poles and zeros to ease the plotting for the Bode plot process. Throughout this process, we demonstrated how the magnitude of a system changes with frequency and how each component, such as simple zeros and poles, contributes a different slope to the Bode plot. Specifically, we observed that a simple zero introduces a positive 20 dB per decade slope starting at its corner frequency, while a simple pole introduced a negative dB 20 dB per decade slope. This behavior was shown at various frequency, showing how the system gain increase or decrease depending on the domain frequency range. The use of logarithmic scaling in Bode plots provides a clear and understanding about the system behavior over a wide frequency range. In the end, this assignment reinforces the importance of poles, zeros, and system gain in shaping the frequency response, which is critical for analyzing and designing stable and responsive control system. Thank you.